Lesson 15 activity. Find the derivative of the following. Y equals cosine of the square root of 2x plus 1. So y prime equals, I see cosine of stuff. The derivative of cosine of x is negative sine of x. So the derivative of cosine of this radical must be negative sine of that radical. But then times, the chain rule says the derivative of the stuff. Now the stuff is right here. And I'm going to write that in a friendlier form for us. I'd really like that to be a power. So 2x plus 1 to the half. And so then the chain rule, the derivative of that 2x plus 1 to the half says the power comes down. Copy the stuff one time, subtract 1 from the power, and then multiply by the derivative of what's in the green parentheses there, which is a 2. So that's our answer. You can cancel the 2's, and I think that's about it. Okay, number 2 talks about Leibniz notation. Pause the video and read through that. Number 3, recall the function e to the all of that stuff from the class demo. We're going to find its derivative using Leibniz notation. So we are going to break down this function into its component pieces, thinking about composition. So I'm just going to fill in the blank over there. The innermost function in this underlined thing is that 2x minus 4. And so would you agree that if I let c equal 2x minus 4, then c cubed is 2x minus 4 cubed, which is part of this original function. And then if you like that, then you would say that sine of b is sine of the thing that we just wrote over there, 2x minus 4 to the third, which is an even bigger part of this. And then finally, y is e to the a, which is e to all of this sine business here. So we now have our original function broken down composition-wise into like 4 smaller pieces here. I guess four smaller functions here. So we're going to find dy dx by using this expanded Leibniz version of the chain rule. So dy dx equals dy dA times the adb times the bdc times the cdx. Again, if you'll allow me to just cancel, like treating these like ordinary fractions, then sure, we get dy over dx. So let's see what we can do. Dy dA means find the equation that says y equals, and then take its derivative where the variable is a. So here's the equation that says y equals, and the derivative of e to the a is just e to the a. You don't need to do a chain rule because it's simply a up there. If you want to say the derivative of a is 1, that's fine. But the point here is that we're not really doing chain rules. We've made the functions as simple as can be, and so we don't actually need to do the chain rule on the individual pieces. Okay, next up, we're going to do this piece now. So we just did dy dA, so now we're moving over here to dAdB. That says find the equation that says a equals, and take a derivative where b is the variable. There's our equation. And the derivative, so dAdB says the derivative of that a equation, derivative of sine of b is cosine of b. Again, no need to do a chain rule, it's just plain b, it's just like a plain x. Okay, moving on, dBdC. That says find the equation that says b equals and take a derivative where c is the variable. What's the derivative of that? 3c squared, easy peasy. And then the last one is here, dc dx. Says find the equation that says c equals and take the derivative where x is the variable. Derivative of 2x minus 4 is plain 2. Just going to be consistent here and say that this was the thing in black. Okay, and according to our big expanded chain rule thing, dy dx is supposed to equal the product of all 4 of these things that we just found. So I'm just going to naively write this product. E to the a times cosine of b times 3c squared times 2. I'm just writing down the big product that we have up there. Now this at the moment doesn't look like our answer because we've already done this problem. It was in the demo. It doesn't look like it yet, but that's because we haven't done enough back substituting yet. So what I'm going to do, I am going to start by substituting c. So I'm going to copy everything else, e to the a, cosine of b, 3c squared times 2. So everything is copied except for the c. And now instead of c, I'm going to put what c is equal to, which is just 2x minus 4. Great. The goal is to make everything just x's. Okay, I think I still want some of that on the page. There we go. Okay, now I'm going to replace the b. So according to this definition, b is c cubed, but again, c is this over here. So really b is equal to 2x minus 4 cubed. So that's what we're going to put right here for this b. So I've kind of run out of space, but I'm going to try to copy everything else, cosine of, but then instead of b, I'm going to put what b is equal to right there, 2x minus 4 to the third. And then we'll copy everything else. Times 3 times 2x minus 4 squared times 2. Sure, you can multiply the 3 and the 2 and get 6, but that's not what we did in the demo, so I'm just going to leave it in its unsimplified form. And then the last thing, I really don't have space, so I'm just going to ask you to finish it on your own, I guess. We're going to replace this a becomes sine of b, but instead of that b, we're going to put 2x minus 4 cubed. So really, a is sine of 2x minus 4 cubed. And so that's what you're going to substitute in right there. And when you do that, you just make that substitution, you should go back and check our final answer to the demo. Fingers crossed, I think that's exactly what we got when we did the demo problem. Okay, number 4. Suppose there are two functions such that lots of information that I don't know what to do with. Find the derivative of this particular function at x equals 1. Okay, h prime of x. Before we do h prime of 1, we do h prime of x. So I'm looking for fundamentally, what is this? Fundamentally, it is an addition here and a subtraction here. Groovy. That means that I can do these derivatives completely independent of each other and put a plus and put a minus. There's a little bit more space here. Okay, so let's tackle this first guy here. 4 times f of x squared. That the derivative of that thing is going to go right in here. Okay, 4 is a constant multiplier. Great, it stays. So next question is, what's the derivative of f of x squared? Well, this is the outer function and this is the inner function. And according to the English version of the chain rule, the derivative of that composition is the derivative of the outer, that's symbolized f prime, evaluated at the inner, that x squared is the stuff that got copied one time, multiplied by the derivative of the inner. The derivative of x squared is 2x. Again, I could not have done this when I was taking my calculus course, but I'm hoping you get to a place where you can. Okay, so that's the first one. Let's move on. We'll highlight this one in green. G of x squared, that's some stuff to a power. That's easier for me. Bring the power down, copy this stuff one time, subtract 1 from the power. I won't put a 1 up there, times the derivative of the stuff. The derivative of the inner function is symbolized g prime of x. Minus, I've got one more highlighter, put it right there. So this one, you can again think about like outers and inners, right? Like it's the derivative of the outer evaluated at the inner times the derivative of the inner. But I will also point out that this thing that I just wrote down is exactly the mixed notation version of the derivative that you can check out in the demo. Okay, so that's it for the derivative at x, but we wanted to evaluate this derivative at 1. So h prime of 1 just says change all of these x's to 1s. Okay, and now finally I'm ready to use the information that was provided. So this thing equals 4 times, all right, f prime of 1 squared, that's just 1. So f prime of 1 I read from the given information, that's a -2 times the 2, I won't put the times 1, plus 2 times, okay, g of 1 looking up is 2, g prime of 1 looking up is -6, minus f prime I'm copying, g of 1, looking up there, is 2. And then g prime of 1, again, is negative 6. And then the last piece to this puzzle is f prime of 2. I'm looking up, I see that that is 10. So I think we're just about done with this here. And now we'll start doing the arithmetic. So this is a negative 16. That's a minus 24. And this is a plus 60 over here. So what do we have? Negative 40 there, and then a plus 60. So I guess 20. Okay, so that's it for this page. On the next page, lots of reading for you to do. I'm just going to run down to the start of the problem. It says, suppose that CE is, so you should pause it and read if you haven't had a chance yet. CE is 20, so we'll mark that one. 20 is this whole thing. And that BC is 5. Great. And it says, let x be the distance shown, and then express the distance DE in terms of x. Okay, so DE, which is this right here, is just 20 minus x. And so that's how far Elvis needs to run along the beach, and then we're going to swim from D to B. Okay, I express the distance Elvis swims, so that's BD, and if we just focus on this triangle right here, we see that it is a right triangle, and 2 of the sides are labeled with an X and a 5, and so Pythagorean theorem comes in there, and I don't know what color, how about black? And so if you do the Pythagorean theorem on this thing, you will find that it is the square root of x squared plus 25. Okay, and now we're told that Elvis's running speed is 6.4 meters per second, and we want the time spent running. So, whoopsies. So I don't know a lot of physics, but I do know that distance is rate times time. And so if I want to solve for t, I have to take the distance and divide it by the rate. And so we're going to take the distance that we went running, that was in red there, 20 minus x, and we're going to divide it by the rate that's given as 6.4 meters per second. So that is how long he spends running along the beach. Same deal now for D, except this is about time spent swimming. So again, it's a distance divided by a rate. The distance swimming is that square root, x squared plus 25, and then divided by this much slower swimming speed, 0.91 meters per second. And then it says, use your answers to write an expression for the total amount of time. So t of x is just going to be the sum of the 2 previous answers. Okay, and now we're trying to reach the ball as quickly as possible. So where should we run to along the beach before we start swimming in order to minimize the amount of time, minimize the answer to part E? And there's a recommendation here. It says avoid the quotient rule. So I think that's a good recommendation. Probably should. I'm the one that came up with it. Okay, so here we go. I guess we'll leave this on the screen. T prime of x equals. Okay, doing the derivative of this 20 minus x over 6.4. The recommendation is to not do the quotient rule, but rather treat this division by 6.4 as a multiplication of 1 over 6.4 times. And now the derivative is really just the derivative of this 20 minus x, and the derivative of 20 minus x is simply negative 1. That is what you would get if you did the quotient rule and did a bunch of simplifying, but there's no reason to get involved in that. Same deal with that 0.91, 1 over times, okay, this next derivative is a little bit tougher, but we're doing the derivative of this thing right here. And so again, imagine that as x squared plus 25 to the half power. We trade it for a fraction power. So the 1/2 comes down, copy the stuff inside, subtract 1 from the power, multiply by the stuff in the parentheses. That's a 2x there. Probably should rewrite that. So this guy right here is really x squared plus 25 to the half. So that's what we were using for this derivative we just did. Okay, so the derivative is done, and we know we're trying to minimize, so that means finding critical points, endpoints. So given that we have to set this thing equal to 0, it's in our best interest to clean it up first. So this is a negative 1 over 6.4 plus 1 over 0.91. Now, the 2 on the bottom here and the 2x cancel. That's great. So this whole thing goes away with this 2. And then this other thing up here is a negative 1/2 power. I'm going to shove that downstairs as a square root down there. Again, just exponent properties. And there is something left over on the top, and that's an x. So that was that x from the very front, from the very back of this thing. So this x right here is all that remains on the top. And we're going to do some algebra here. We're going to set this thing equal to 0 and solve for x. So we've got two terms with the plus sign in between. I'm going to add that 1 over 6.4 to both sides. Then we're going to cross multiply. If you prefer, you can think of it as multiplying both sides by both denominators. I don't like that there's a square root, there's x's inside of that square root, so we are going to square both sides right now. So different color here, squaring this and squaring this, the entire, both sides. Okay, so let's square both sides. 6.4 squared. 40.96, so this is 40.96, and then the x is also squared, so don't leave it as an x, it's an x squared now, equals, okay, now the 0.91 is getting squared, 0.8281, and then when I square this radical piece, the radical disappears, so we get that. And then we're going to distribute on the right-hand side 0.8281 x squared plus, and we're going to multiply this thing by 25. Okay, we're going to bring the x squared term from the right-hand side over to the left-hand side by subtracting. I'll just write that out here. So we're subtracting 0.8281 x squared from both sides. Trying to get my x squared terms together. Okay, so let's do that here. 40.96 minus 0.8281. This tells me how many x squareds we have, 40.1319. Equals this constant on the right-hand side. You'll notice that the calculus was actually quite a bit easier than the algebra here in this problem. That's not so unusual. Okay, 2 steps left. We need to divide both sides by this 40 and change. So I'm expecting a number right around a half. Let's see what we get here. So I'm gonna be super fancy here. Hang on. I'm gonna take this thing and hit it with a -1. That puts it on the bottom, and then I'm gonna multiply by 20.7025. Fancy, fancy. That's why they pay me the big bucks. Okay, I don't feel like writing all of that out. I'll say 0.516-ish. Okay, and then square root of that number. So second square root second answer, 0.718. Technically plus or minus 0.718, but of course we're only going to run in the positive direction on the beach. It wouldn't make sense to, so I think, so we're running, how are we running here? So this is the 0.7, positive 0.7 is what we found out, hopefully is the answer. Negative 0.7, I guess, would make it that, which would mean Elvis would run here all the way past the ball and then back and, no, past the ball and then start swimming that way, and that wouldn't make any sense. That's clearly not the optimal path to take, shortest time path. Okay, so I think we've got our answer here. But let's really justify this hardcore and make sure that indeed that is the minimum time and not the maximum time, right? It could be the worst possible path would be putting a 0.7 here. So what are we going to do? We're going to do endpoints and critical points. This is like x has to live someplace between like 0 and if x were all the way out here, it would be whatever that distance was, 20, I guess. So I think we've got our problem on this closed interval. X for sure is something between 0 and 20. If x is 0, that would mean Elvis would run all the way over to here and then shortest possible swim path. If x was 20, that would mean that 20 was this entire thing, and this line would really be this line, and so Elvis would say, forget running along the beach. I'm taking the shortest distance, even if it means swimming the whole way. So I think we've got our standard process for optimizing a continuous function on a closed interval. So here we go. We've got x's, and we've got t of x's, the original function, not the derivative. And we're going to put in here the critical number, 0.718, and we're also going to put in here the endpoints, 0 and 20. Critical point here, endpoints here. And then we're just going to plug these things in to the original function. So since we're doing 3 function calls, I'm going to type the original function into my y equals. So that's this one right up here at the top. Right at the top. Okay, so here we go. Parentheses, 20 minus x, close the parentheses, divided by the 6.4, and then plus square root x squared plus 25, close the parentheses, divided by 0.91. Okay, and then second table set. I want it to ask me, and then second table. Let's come over here and store this number right here. So I will store this as A, just so I don't have to retype it, and also so I can get the most accurate answer possible right here. So I just type alpha A, and it says, oh, 0.718 and change, you bet. 0 there, 20 there, those are the endpoints. So we're going to grab those numbers from the calculator. Okay, so these times that I'm writing down are in seconds, so 8.56 seconds for that path. The next one, 8.62. And then 22.65. I think that's good. So that 22.65 is the, swimming the entire way, not running at all. 8.62 is running all the way to the point on the beach that is closest to the ball and then swimming the shortest distance possible. Turns out that Elvis the dog can save a little bit of time, not a whole heck of a lot, by running to the spot that's 0.718 meters away from the spot that's closest to the ball, spot on the beach that's closest to the ball. Okay, so that means that if we wanted to actually tell Elvis how far to swim, it should be 20 minus the 0.718. Sorry, how far Elvis should run. 20 minus the 0.718, because x was not the distance to run, but x was the distance left over that he didn't quite run. He stops right there at the 0.718 mark. So Elvis should run 19.282. I think I've got that. So that's how far Elvis should run, and then make a beeline for the beach ball by swimming directly to it. Okay, on the next page, it says suppose C is 40 now, and BC is 5. And then we're going to do the same calculation again, but I'm not going to start from scratch. In fact, the only change is that the 20 became a 40. So I'm just going to jump. So you could just put a 40 right there, but I'm actually going to jump even farther and see if I can figure out where did that 20 go in this problem. So take a look. Imagine that this is a 40. When we took a derivative, that 20 completely disappeared, right? The very first thing we did, we put the 6.4 out in the front, and then we multiplied by the derivative of this, and the derivative of this was just -1. Well, guess what? When you put a 40 there, the derivative of this is still -1. And so that means that our function, so I guess I'll write it here. I'll write the function properly here. This t of x function is 40 minus x, and everything else is the same. But when you take the derivative of this function, t prime equals same as previous page, which means that the optimal x is the same as on the previous page. It's still 0.7 meters shy of the sort of perpendicular point on the beach. So even when this is a 40, Elvis should still run to the point, which is 0.718 meters shy of point C, the spot on the beach closest to the ball, which is kind of cool. So this is based only on his relative running and swimming speeds, and it made absolutely no difference how long the beach was. 20 meters, 40 meters doesn't matter. Now the 25 matters, right? Like both of these had a 5, and that 5 ended up being a 25, and that 25 ended up being part of the derivative, right? It's there, and it had some impact when we solved the equation. But it turns out that horizontal distance does not make any difference at all. Okay, suppose CE is 10 and BC is 10. All right, so CE is 10, that's the horizontal, and now BC, that's the vertical there, that's 10. And now where should we run to? Okay, so let's see if we can do this quickety-quick. All right, so in this formula up here in green, I'm changing this to a 10. And this 25 came from doing 5 squared, but now it's going to be 10 squared. So let's make those changes down here. So this t of x function, the 40 becomes a 10. And then this should have been x squared plus 5 squared, but now it's x squared plus 10 squared. And divided by the same 0.91. Now I can't just look at this and know, oh, here it's going to be the same answer, or here's how this answer is going to relate. But a lot of the calculations are the same, right? So t prime of x is -1 over 6.4, just like before, plus, okay, let's be really clever about this. So the 0.91 is on the bottom. There's going to be a 2x and a 1/2 that are going to cancel just like before. There's going to be a square root down here, x squared plus 100 now. And up on top, there was an x before, there's still going to be an x. And so we're sort of saving some time here, recognizing the similarities between this problem and the other. So I'm going to kind of just skip a little bit of the algebra here and say what we're going to do is take 0.91, square root of x squared plus 100. That's going to equal 6.4x. Then we're going to square both sides. Okay, and so this is still 40.96 x squared. This is now x squared plus 100, so that 100 is going to make a difference. Equals here, so 0.91, what was that? Was that 8281? Let's make sure we've got that right. 8281, super. All right, and then we're going to multiply. Okay, so then very little new, but I think this is one of the spots where it becomes new. When I distribute here, 0.8281 x squared plus, and now 100 times this is 82.81. Guess I really could have jumped almost to this step on the previous page because then we're going to subtract, and it'll be the same subtraction we did before with the x squareds. So where is that? 40.1319. 40.1319 x squared equals, and then the only difference is this 82.81. So really that number is the only change, and then we do a division here and then take a square root. So let's do that. Okay, so we're taking our 82.81 and dividing it by 40.1319, and then we're going to take the square root of that thing. So this is our new critical point, 1.444-ish, 1.436. And so what that would mean would be that instead of stopping 0.7 meters away from this closest spot on the beach to the ball, he's going to stop farther away, right? What was it? 1.3 something, 1.436. So one observation here, some of you might have seen this, but there is a nice relationship between this 1.436 and the 0.718. Pause the video here if you want to think about that relationship, 1.436 compared to the 0.718. But if you haven't seen it, I will say that it sure looks like one of these numbers is double the other. And I'm guessing that is not a coincidence. So we can verify that over here because I think I still have A typed in or stored as the 0.7 number. And look, lo and behold, it's perfect. It's not just to the nearest, thousandth. It's perfectly double. So what happened over here? Well, we decided that the 40 doesn't matter, right? 40, 20 makes no difference. In this problem here, we made it a 10. So I'm guessing that 10 shouldn't matter at all. But what did we do to this distance that the ball is from the beach? Well, it used to be 5 in the basic setup of this problem. And then we made it 10. Hey, what do you know? We doubled the distance that the ball was from the beach. And that ended up doubling how early he should stop, right? How far away from the closest beach point to the ball he should stop. And that's kind of neat. So you might experiment with that if you're interested in pursuing this further. Is it true? Like if we triple, if you made this 15 instead of 10, would we just get triple this 0.718? Something for exploration.